All right, so in class we ended up talking about electron configurations, and I said that we would be able to figure out if something is magnetically active or not magnetically active. This is known as paramagnetism or diamagnetism. So let's talk about this. So we can have paramagnetic or diamagnetic. So diamagnetic. Diamagnetism and paramagnetism. And paramagnetic compounds have unpaired electrons. So paramagnetic have unpaired electrons. And are attracted by a magnetic field. Are attracted by a magnetic field. Whereas diamagnetic the substance has no unpaired electrons, or all the electrons are paired up, so paired electrons, and it's actually slightly repulsed by a magnet, are slightly repelled by a magnet. Or a magnetic field. And they use an apparatus to figure out if something is diamagnetic or paramagnetic. It works almost just like a conventional balance, except they have a magnet hooked up to it. So what they do is you have your sample. So this is a sample, and you have it attached to some balance. Put weights on this balance, and what they do is they get the weight of the sample, and then they put it in an external magnetic field. And what they do, they kick on the magnet and they see what happens. If it's pulled further down and it appears to be lighter, then it is paramagnetic. And if it happens to end up shift up, so this is repelled by the magnet, it ends up being diamagnetic. So they kick this on and they see what happens to the sample's weight, or excuse me, its mass. So we're going to ask the following then. We're going to ask if we're going to go through two examples on two molecules. We're first going to look at carbon. We're going to figure out if carbon is diamagnetic or paramagnetic, and then we're going to consider zinc. So let's look at example is a lone carbon atom. Dia or para? Magnetic. So the first thing we need to do is consider carbon's electron configuration. Carbon has a total of 6 electrons, so we have the 1s2, 2s2, 2p2. Now, let's draw out the electron configuration diagram. Again, on our axes, we have energy increasing. The lowest energy orbital should be the 1s, followed by the 2s. And then we have 3 p orbitals, the 2py, 2px, 2pz. Okay, now that we have our orbitals, let's start filling them. Up, down, up, down, up, up. For a total of 6. Since we have 2 unpaired electrons, this system is paramagnetic. So it is paramagnetic. Let's consider another example, a more tough example, where we're looking at zinc in this case. So we're going to ask the exact same question, except we're just going to change a lone carbon atom to a lone zinc atom. So let's write the condensed electron configuration for zinc. If we look at the periodic table, we can see that it is argon that is closest in terms of a noble gas. So we can put argon, and then we just have the remainder valence shell. We have the 4s2, 3d10. And we can write out a condensed electron configuration diagram where we're only going to consider the valence electrons because, hey, those are the important electrons. We have the 4s, and then we will have a total of 5 3d orbitals. 1, 2, 3, 4, 5, 3d. And now we have to fill those with 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did something really bad. I didn't follow Hund's rule and the Pauli exclusion principle. I should have filled these ones first. All right, if we look, all of our electrons are paired up. So we have a diamagnetic system. In this case. All right, so we're done talking about electron configurations, but we started talking about the periodic table and the way that the periodic table is shaped. There's actually a wide variety of information that's contained in the periodic table, and these are known as periodic trends. What you can do is by glancing over at the periodic table, you have a better idea of, let's say, an atomic radius or the size of an atom. You know which one is more electronegative or which one's more likely to pull electron density away. You know which one has a greater electron affinity where it can pull electrons towards it, or which one that has a higher ionization potential or the ability to give off electrons. So we're going to start talking about these trends, and for the remainder of this lecture what we're going to discuss is about effective nuclear charge. And what is effective nuclear charge? So we're going to start a discussion of effective nuclear charge. Effective nuclear charge. Or Z effective, we're going to call it. The nuclear charge is often given the symbol Z for some reason. And we're going to ask a question. As we increase the atomic number, what happens between the interaction between the electron and the nucleus? So, as we increase in atomic number, what happens between the interaction between the nucleus and the electrons. So we're going to look at that interaction. And what this depends on is the distance between the particles, so between the nucleus and the electron, and also this effective nuclear charge. So distance between the electron and nucleus, and also the charge experienced by that electron from the nucleus. charge experienced by the electron from the nucleus. And this is exactly what the effective nuclear charge is. So this is Z effective. That should be a subscript. So it is the effective nuclear charge. And what it is it's the charge experienced by an electron from the interaction, or the attractive interaction of the nucleus and the repulsive interaction between that electron and all the other electrons in the system. That electron and all other electrons in the system. All right, and the way that this is calculated is it considers two things. It considers the charge on the nucleus, and it considers another parameter known as the shielding constant, which is given the Greek letter sigma. And we'll talk about what shielding is in a moment. So, what we have is Z effective. The way that it is calculated is Z effective is equal to the nuclear charge minus the shielding constant. So, this is the effective nuclear charge I don't know if this does well to see it. This is our nuclear charge or the charge on the nucleus, and this guy, the sigma, is a shielding constant. So let's discuss what shielding actually means. So what we're going to do, we're going to consider the fluorine atom. So shielding. Given that symbol sigma. And we're going to consider the fluorine atom. Consider F atom, where we have our nucleus. And if you look at the periodic table, what you find is for the charge of the nucleus in the fluorine atom, it is a +9 charge. And we're going to express this in the Bohr model of the atom. So we're going to have another shell. This is n is equal to 1, and there are 2 electrons. N is equal to 1, and there are 2 electrons bopping around in that orbit or in those set of orbitals. And then we have n is equal to 2, which can hold a total of 8 electrons. In this case, it's 7 electrons because it's the fluorine atom. And what you can note is we have this nucleus. We have these orbitals hanging around it. And the ones in the n is equal to 1 state, they experience a greater amount of charge of the nucleus. They're closest to that nucleus. However, those in the n is equal to 2 state are kind of protected from the charge on the nucleus because there's that n is equal to 1 state in between. So they absorb some charge, let's say, and then the electrons in the n is equal to 2 state don't see as much charge compared to the n is equal to 1 state. So if we look at the orbital, and we look at the Z effective, what we find is, let's look at the 1s, 2s, 2p. Those are the orbitals that are available to a fluorine atom. If we look at the Z effective, or the effective nuclear charge, we find it as 8.650 for the 1s state, 5.128 for the 2s state, and 5.100. Excuse me, for the 2p state. So what we can see is as we get further and further away from the nucleus, this Z effective starts to fall off. And it's not really because we're getting further and further away from the nucleus. It happens that these inner electrons shield the outer electrons. So the electrons in the 1s orbital take the first hit from the charge, pow, and then these guys are left over with what remains. So let's explain what we see. The electrons in the 1s orbital screen or shield the electrons in the valence shells, 2s and 2p orbitals. And this lowers Z effective for those orbitals or those electrons. And Z effective can be calculated in a quick and dirty way. This isn't the actual way to calculate Z effective. The actual way was when we looked at the nuclear charge and we determined that shielding constant. However, there's a quick and dirty way to do it that isn't quite correct, which we'll denote as Z effective prime, and how to calculate it. So you can kind of use it as a way to approximate what the effective nuclear charge is. So Z effective can be thought of roughly as the following. We're going to call it Z effective prime because it is not quite the exact same thing as Z effective. Z effective is equal to the charge on the nucleus minus the core electrons, which we talked about last time. What is a core electron and what is a valence electron when we were discussing electron configurations. So now what we're going to do, we're going to calculate the effective nuclear charge, or the approximate effective nuclear charge, Z effective prime, for an orbital in a fluorine atom. Example, calculate. The effective nuclear charge, the approximate effective nuclear charge of an electron in the 2p orbital and 1s orbital of a fluorine atom. All right, so we can do that. Let's do the 2p first. 2p, what we have for that one, it's z effective prime is going to be equal to the core charge, or the charge on the nucleus minus the core electrons. So in this case, we have +9 because we have a fluorine atom, minus core electrons, or the inner electrons, the ones that are closer to the nucleus. So what we get as a value is a +7, which isn't exactly correct. If you remember the actual values for this, it was more close to 6. But it's an approximate way to think about it. Then let's consider the 1s. We have z effective prime. It's going to be equal to, again, that +9 minus the core electrons, or the ones that are deeper than the 1s. Unfortunately for fluorine, there aren't any electrons that are deeper than the 1s. So the number of core electrons for a 1s would be 0. So that means we have a +9 approximate z effective, which is fairly close. We have 8.650 for our z effective for the 1s, so if we round up, it works out pretty well. But what you can see is the effective nuclear charge for the 2p is greater than that for the 1s. All right, so I said that we were going to discuss some periodic trends, which we will get to in a moment. But we have to ask ourselves, why do the actual z effective and this approximate z effective prime, why do they differ? Well, we're making one approximation with our atom. We're assuming the Bohr model of the atom is correct, which isn't quite true. We know that we have this kind of hazy electron density around our atoms in the modern atom. So that's pretty much why. So the reason why do z effective and z effective prime differ? And one of the main reasons is if the Bohr model were true. So the Bohr model. So we're using the Bohr model. If it were true, then in fact our z effective would equal our z effective prime. Unfortunately, it's not. And the way that it really is there's electron density around this atom. So there's a probability of finding the electron. And what we can do, we can actually plot this. And what we're going to have along here is the probability, or the electron density, the probability of finding an electron. So we have radial electron density. And we have the distance from the nucleus. And if we consider a 1s, we actually get something that looks kind of like this, where this maximum is what's known as the Bohr radius, and that's actually that orbit, the distance from the electron and the nucleus in the Bohr model of the atom. That's exactly what this is. So this is a 1s. Now I'm going to draw in red what the probability electron density is for the 2s. What you'll find is as we get closer to the nucleus, it's likely that one of the electrons in the 2s is found here. But then we find as we get further away from the nucleus, we have our maximum. So this is our 2s. But the reason that Z effective isn't exactly equal to Z effective prime is because for the 2s and even the 2p orbitals and higher energy orbitals, sometimes they spend a little bit of time around the nucleus. And since they're shifted towards the nucleus a little bit, they see some of that charge. They actually help screen one another. The 1s and the 2s help each other screen. So that's exactly why if we're looking at the 1s of a fluorine atom, it isn't exactly 9, because the 2s slightly shields the 1s for a little bit. All right, so now let's talk about some periodic trends. So that's what this is all about, trying to get some trends. So what we're going to do, we're going to keep track of the periodic table. We're going to go across from left to right. So what we're going to do, we're going to keep track of Z, our effective nuclear charge. We're then going to look at the valence, Z effective prime, and then we're going to look at the valence, Z effective. And we're going to look at this for a variety of different elements. We use red because my marker seems to be dying. First, going to look at lithium. Lithium has 3+ effective, or a nuclear charge. If we calculate the Z effective prime of that, we find it as a +1 charge. If we actually look and calculate and experimentally determine the effective nuclear charge, we see that it is 1.28. Let's look at beryllium next. Beryllium will have a 4+ charge. If we look at the approximate Z effective, we get a +2 charge. If we look at the actual, we find that we have a 1.19 charge, or a Z effective. Let's keep this going. All right. We then have boron. Carbon, nitrogen, oxygen, fluorine, and then we'll do neon over here. So we need a few more divisions. That we can do. Divide. All right. And then we're just going to increase by 1 for each one of these. 5, 6, 7, 8, 9, 10. These values for the Z, approximate Z effective, are just going to be 2 less. So we get +3, +4, +5, +6, +7, +8. And now, if we look at the actual values, 0.242, 3.14, 3.83, 4.45, 5.10, 5.76. What we can see is as we move from left to right, that our Z effective, our effective nuclear charge, is going to increase. What about as we go down the periodic table? Well, let's see that. What we're going to do, we're going to keep track of lithium, or just the first group, the alkali earth metals. We're again going to plot the exact same thing. We're going to be looking at Z. We're going to have the valence, Z effective, prime, and then we're going to have the actual Z effective. And then we'll have for lithium, sodium, potassium, rubidium, and cesium. So we have lithium, Li, sodium, potassium, rubidium, cesium, 3, 11, 19, 37, 55. And then if we look at the approximate Z effective, or the one that we can calculate from those slight parameters, what we find is it's +1 across the board. Now, what about the actual effective nuclear charge? Well, for lithium, it's going to remain the same, 1.28. For sodium, it'll be 2.51. For potassium, it'll be 3.50. For rubidium, it'll be 4.98. For cesium, it'll be 6.36. So, an important point is it looks like our approximation, our Z effective prime, is actually not working out. However, we do see a clear trend as we go down the table. And what you see is Z effective increases as we go down the table. The reason it does is we're accumulating a larger positive charge on our nucleus. So that's increasing. So there's going to be a greater amount of charge seen by the valence electrons because we keep increasing the charge on our nucleus. All right, so what do we see as a periodic trend? Well, this is our periodic trend then. So, as we go down the periodic table, Z effective is going to increase. As we go from left to right, our Z effective is also going to increase. So Z effective, as we go this way on the periodic table, increases. As we go down the periodic table, it also increases. So next time, what we're going to talk about, we're going to go into some more periodic trends. We're going to discuss a little bit more about Z effective. We're then going to discuss atomic radii, ionization energies, and finally get into electron affinities and electronegativities. And then we'll be on our way to start actually writing out some Lewis structures and really discussing more about chemical bonding.